Okay, so in the last video, I was giving you an introduction to work, and the main gist of what I wanted you to get out of that was that if you give something some kinetic energy, or give it zero kinetic energy, and then apply a force on it afterwards and watch what happens, you can see how work affects something. For example, this bead was given a certain initial kinetic energy so that it had a velocity to the right. And then after that, we applied a constant force, F, and in the general direction of the displacement, or the velocity, and the kinetic energy increased. That's called positive work. Whereas over here, we gave this apple an initial kinetic energy up, and then after that, what did I say? We gave the apple an initial velocity up, and after that happened, then only the force of gravity was acting on it, in this case in the opposite direction of the displacement or the velocity, and this would cause the apple to slow down, decreasing its kinetic energy. This is called negative work because it's taking energy out of the object. So, oops. Alright, so if you want to put that mathematically, work is one form of work is the change in kinetic energy. If kinetic energy doesn't change, then no work must have been applied to an object. And so you can really just take the form of kinetic energy, 1/2 mv squared, and do 1/2 mv squared final minus 1/2 mv squared initial. I just distributed it, or undistributed the 1/2 m. And this is called the work kinetic energy theorem. To put it in words, it's basically the kinetic energy after the network is done on something equals the kinetic energy the object had before plus the network done on something. And so remember that we could actually this could actually be less. The kinetic energy after the network is done could be less than the kinetic energy before. In that case, negative work would have been done. Energy would have been taken out of the object. So we're going to use this a lot. In fact, this is going to be also used in addition to potential energy, which we'll introduce next chapter, chapter 8. But we're going to use this a lot. Work is the change in kinetic energy. Very powerful statement. And what happens if the force applied is not constant? What happens, unlike gravity or unlike a constant push, what happens if the force depends on your position? Well, then the expression for work is slightly more complicated. It's actually the integral of force with respect to x. And you can see that if we integrate over a constant force, then the f comes outside of the integral. And the integral of just dx is x. So this becomes f times x final minus x initial, which is really just the displacement f delta x. And if you call initial position 0, this just becomes f times x, or f times d. So that's the constant, that's the work due to a constant force. But sometimes this f is not constant. Sometimes it has an x in there, as we'll see very soon with the spring force. So, and as you can see over here, we have a f of x versus a delta x graph, and we have a function, and it's pretty obvious that this force is not constant with position. It looks like as your position increases, the force increases with some interesting progression, and so the work done is the area under this graph. That is what the integral essentially tells you, the area under a graph. So let's actually discuss a very useful, common non-constant force, a force that depends on position. And this force, this little law, is called Hooke's law, and it describes how a basic or a simple spring behaves when moved. Hooke's law tells you that F equals negative kx, and just to minimize some confusion, a lot of people think that the negative is attached to the k because of the way it's written, but it's more intuitive to think of the negative as attached to the x. K is just the spring constant. It tells you how strong a spring is. So it doesn't make sense for a spring to be negative strength, negatively strong, but it does make sense to have a negative displacement. So take a look over here. We have a block attached to a spring, and we let it go so that the spring basically relaxes. So it's not compressed at all, and it's not stretched. So we call that the equilibrium position, and we say that x equals 0 there. And as you can tell, it's not moving because at the equilibrium position, the spring is relaxed, so there's no spring force on the block. Well, what happens if we start to pull the spring to the right, stretching it out? X increases, X becomes positive, and the spring wants to pull the block back to equilibrium, and so the force is acting in the opposite direction of the displacement. That's what the negative is for, and that's why the negative really makes more sense to go with the x, because a spring force always pulls back towards equilibrium. So if you stretch it out this way with a displacement d, the force will pull back in the opposite negative direction. Vice versa, if you push on a spring to compress it, its displacement is negative, but the force pushes back against your hand, trying to bring it back to equilibrium in the positive direction. Long story short, the force of a spring always acts in the opposite direction of the displacement. And so what you could do, just like we did with the apple for gravity, give it some kinetic energy and watch what happens. So if I were to like just pull this, well, let's do the compression. If I were to just push the spring and give it some kinetic energy, you can quickly imagine that as it's compressed, like as you, all right, let me start over. So the spring starts here, right? Sorry, the block starts here. You push it, give it some kinetic energy. As soon as your hand leaves, what's going to happen? Well, the block is moving this way, and it's going to continue compressing the spring because it had some kinetic energy, but the spring is going to be pushing back with a force to the right, and so this block is going to slow down. Slowing down does what to kinetic energy? Yeah, right, it drops it. Kinetic energy is the energy of motion, of speed, and so if we're slowing down, the kinetic energy is going to decrease. Next chapter we're going to talk about where that kinetic energy goes. It's a fun little term called potential energy, but we'll get there. Anyway, so that will explain why. That will basically explain this negative, why that was negative work, because we're taking energy out, right? You push the block, give it some kinetic energy, and then just like gravity was acting down while the apple was moving up, which was negative work, taking energy out. Whenever, as this block is moving into the spring, compressing the spring is pushing back in the opposite direction, causing negative work to happen, sucking out the kinetic energy. And we can get this really easy using some calculus, which, because we're approaching the 9-minute mark, I'm going to do in the next video. So get ready for some calculus, and then we should be able to finish the last slide with power as well in that last video. So, alright, so I'll see you soon.